Hello, in this video I will analyze a dataset of 900 confirmed monkeypox cases. This is a video for beginners, so I will use some very basic functions for data exploration that I almost always use when I investigate a new dataset. We will do some cleanup steps and data manipulations and then produce a bar chart of the countries that have the most cases so far, and in the end also create a pretty looking map. The data comes from a Google sheet called Monkeypox Public, and it currently has over 1,000 entries and is almost daily updated. It has some summary statistics on confirmed and suspected cases by country, and it also links to a GitHub page that shows you how you can load the data directly into R by using the HTTR package and simply copying this code into your R console. The latest version is of June the 4th and it has 900 confirmed cases. Another way how you can access the data is to go to File and then download either as Excel or as CSV. With the ls function, you list all the objects in your current workspace, and with rm for remove, you can remove any object. So I start with a blank slate. Then you load the HTTR package with the library function. If you haven't installed it yet, then use install.packages HTTR. And then the read CSV function creates a data frame object called df that has 1107 rows and 31 columns. The dim function gives you the dimensions of this data frame. What you can also do is set working directory to the location of your R script. So what I'd like to do is I have the Excel file in the folder where the R script is. And now with get wd, you get the working directory, which is this folder. And with list files, you can see that there are the Excel files of various dates in this folder. And with the read Excel function from the read Excel package, you can load the first sheet of this Excel file. The function just needs to know the path where the file is. And for this, I merge together the current working directory with the file name. And I do this with the paste 0 function. So this is the path to the Excel file. And here you can see it also loaded the data with over 1,000 entries and 30 columns. Here are a few functions that I always use. Of course, the dimensions to see how big the data frame is that I'm working with. Then I often use names to get an idea of the data. So we have an ID, a status, and then location, city and country, age, gender, and then some dates, confirmation or onset of symptoms, the symptoms themselves, information on hospitalization and outcome, contact information, travel history, some notes, and then sources. With the arrow keys, you can go up and down to the functions that you used before, and we can change the names to str to get the structure of the data frame. And here it lists all of the 31 columns again and gives you information on whether it's character data or integers. So the IDs are running numbers from 1 to 1107, and most of the data is characters. And here you see one difference between the CSV function that read the data directly from the website. It produces a data frame, which means when you use head on this data frame, you get the first 6 rows of all the columns. But if you load the data with the read Excel function, it creates a tibble. And the difference with a tibble is when you use the head function, it will only fill out your console depending on the space it has, and then it skips the other variables and it doesn't give you a preview but just lists them. But one thing you can do is use the view function with a capital V to get a table where you can scroll through all the columns and rows, and you can even filter for certain entries and then only look at those. When you explore the data in the console, you can use the history tab to look at the functions that you used, and you can also copy them to the source code. So now I know that these functions were kind of useful to explore the data. And one more crucial thing would be to look at missing data. So for example, you can see the IDs are always there. There seems to be always a status and a location. But then for age and gender, there's already some missing data and A's. Also for symptoms, there's often gaps in the data, and for hospitalization as well. So one quick way to check this for all of the columns of the data would be to ask whether the data frame is NA. And you can do Control Enter to execute the function. And what it does, it turns the whole data frame into a true or false matrix, depending on whether there is missing data or not. So false means no, there's real data. But if it's true, then here we know there are gaps. And true and false behaves in R like 1 and 0. So imagine you have a vector with 5 entries that are combined with true, false, false, true, true. And of course you could have also written that with capital T and Fs, which produces the same vector. If you build the sum of this vector, you get 3, because there's 3 times true. And more importantly, if you ask for the mean of the vector, the average, you get 0.6, because 3 out of 5 entries are true, so that's 60%. So once we ask whether our data frame is NA, we can use the call sum function to add up all the truth in the data frame. And here it tells me that the call sum function cannot be found because it's actually call sums. Now you see 0 missing data for ID and status, but for location, age, it can be a lot. Now I could divide these numbers by n row data frame, which is 1106. And if I divide these sums of missing data by the total number of rows, I get the percentage of missing data. And you could round that after multiplying it with 100 to get some proper percentages, and then also sort it to find which columns have the most missing data and which have no missing data at all. Within the sorting function, if you hit tab, you see that there's a function argument called decreasing. If you set this to true, then it will give you the columns with most missing data first. And if you paid attention, then the call sums divided by number of rows, you wouldn't have needed if you changed this to call means. This then gives you the exact same results. So unfortunately, most of the columns have missing data, so we won't be able to do a lot of analysis on age, symptoms, or gender. Most of the analysis will be based on cases per country. So now after you did some data exploration in the console, you can copy over the functions that worked for you the best into the source code. If you want to analyze an individual column of your data, you can of course access it with the $sign, and then it already shows you a preview of what columns there are. And I want to use the status with the table function to investigate how many confirmed cases there are, discarded and suspected. And for this analysis, I only want to use the confirmed cases. If you're familiar with the tidyverse, then you can pipe your data frame into the count function and then count status as well. And it gives you the result in a slightly different format. Okay, next I want to create a data frame called Monkeypox that has cleaned up names, because I don't like these spaces and parentheses and slashes. And also I'm more used to working with data where the first letter is not capitalized. And for that I use the raw data frame, which I still have as a backup. And I pipe it into a function from the janitor package that's called clean names. And sometimes it's good practice to include this information by using a double column. So now R or other users of your script will know that this function comes from this package. And after this function is applied, I will filter for status column being equal to confirmed cases. And what the janitor clean names function does, it will turn all function names into lower capital, and it replaces spaces and unknown signs to an underscore. So now this is how the Monkeypox names look. No brackets anymore, all lowercase columns, and the status should now only be confirmed cases. So let's find out where most of the cases happened so far. There are different ways to do that. You could use the table function on the country column and you get the results alphabetically in a table format. You could always try to turn that into a data frame. Then you will get 2 columns, one for the first variable, which is the country, and the frequency. If you don't want the table results to come out alphabetically but sorted by values, you can sort the table, and again you could use decreasing equals true to get the country with the most cases first. If you use the table function on a column that has missing data like age, you won't notice that unless within table you use exclude equals null. So now all the NAs will be shown, which is 750. And here you see the advantage of using the tidyverse function count. If you use the count function on age, it will always show you the missing values, the NAs. And if you count the countries, it will keep the table format from the Monkeypox data frame structure and only print out the first 10 rows and tell you how many more countries there would be. And within count there is a function argument called sort, which you can set to true, and then it also sorts automatically by most cases to least cases. Whenever you create such results, you could pipe it into the view function and then see all of the entries. But now the question is, how do you turn this result into a bar chart for some data visualization? So one way to produce a bar plot is with ggplot and the geom_bar function. What you do is you either pipe the data frame into the ggplot function, or within ggplot you specify that the data is monkeypox, and then you go into the mapping where you map the aesthetics. For example, here on the y-axis you want to have the country. And what the geom_bar function does with stat equals count, it automatically counts all the entries in the country column and produces the n value and then plots them alphabetically. However, what I prefer is the geom_col function that works on the results directly, and it's also easier to understand. So imagine you have the results of the count function with the country and an n value. What you would do is, after you created these results, you use ggplot and you do the aesthetics mapping where x is now the n and y the country, and then you add with plus the geom_col geom. This is a good first result, but what I want to do now is first sort them by decreasing values, and second only show the top 10 countries and lump any other country that has fewer than a certain number of cases into an other category. Okay, so how can we sort the countries by decreasing number of cases? You might think that including the sort argument within the count function would do the job, because now the country and n that we use for the ggplot mapping comes in decreasing order. But if we execute these 3 lines of code, you get the exact same plot, because the countries in this results data frame come as character, and by default ggplot will sort character variables alphabetically. Therefore we must turn them into factors that are sorted by decreasing number of n. And here I load the 4cats library, which comes with the fct reorder function. And what we now do with the results of the count function is mutate, so transform this country column first into a factor. So now if we run this code, you see that the countries are now a factor, and factors can be reordered by a second argument within the fct reorder function, and this is n. So now if you ask for the structure of the last value, which is the table that was created by counting and mutating the countries into a factor, it tells you it is a factor with 32 levels, and Austria and Hungary are the 32nd and 31st entry because they only have one case. And if you use this now within the ggplot function in geom_col, the values come out in this order. If you use a minus in front of the n within fct reorder, they come out the other way around. Another very useful function from the 4cats package is the fct lump function, and it allows you to lump other countries together. If you turn the country column of the original data frame, monkeypox, into a factor, we can create another column called country other within this mutate, where we lump all countries together that are not in the top 10. The pull function extracts this column. So if we run this code, we get the results, and now you see that often an other entry appears, and the table function will tell you that these are the top 10 countries with cases, and then if you lump all the other countries together, you get 70 cases in the rest of them. So Belgium is the top 10, that's the cutoff, and everything else gets lumped together. And if we follow this lumping together and plot it with geom_bar, you see that it worked. You only have 10 countries and then other, but we would still have to do the reordering, and that's best done on the count data. Okay, so the next steps are a little bit complicated because I'm using the add count function, and what it does on the original data set, so we still have the 900 entries, but now every entry has already the count of the country. So we're expecting 214 cases for England, 143 for Portugal, and this number I will use to reorder the whole data set by decreasing n, and I follow this up by creating a new country column that lumps all other countries together. And another argument in the fct lump function is, how do you want to call this other factor? And here I want to paste together other countries plus the number of them. So it should then say 22 other countries, because we know there are 32 and the top 10 are here. So we can ask for the unique countries, which are these 32. We can ask about the length of this results vector, which is 32. And when we want to lump everything but the top 10, we subtract 10, and then paste 0 will look like this, 22 other countries, maybe with a lowercase o. So this would be the result. If you don't use -n, what you get would be a resorting like this, and the other category will always be outside your order. So I prefer to first reorder with decreasing values, then lump everything together with other, and it comes out like this. But with scale Y discrete, you can flip the limits upside down. So in reverse order, this is a really nice looking chart of the top 10 countries in 22 other countries. If you want to make this a little bit better looking, you can fill the bars with a color. These are factors, so they will come out in 11 different colors based on a rainbow gradient. The color black will then show you that it has black borders. Now, we don't need the legend because the label of the country is already attached to the bar, and you get rid of this with the theme legend position equals none. I will also use the theme black and white, and I want to label these bars. And for label, I can use N, you have to map it, and I fill it with the same color as before. So maybe it's better to show this in different steps. You could already do the aesthetics mapping in the original ggplot function by saying that the label is supposed to be N, and keep in mind we're working on these results, these 11 entries with country, other, and the count. So adding geom label would look like this. I want to move the label a little bit to the right, which you can do with the nudge X argument. I want to set the size to 4, and I want to fill the label with the same color, but make it a little bit more transparent. So use an alpha of 0.5, but still keep the outside border black. So that's how it looks. So then with theme black and white and legend position equals none, you get this. And of course we have to again change the order and then also set a limit on the x-axis. Now within labs you can add a title and change the x and y-axis values, which are not necessary. So in the title I want to paste this together, which holds the number of confirmed cases, which is the n row of the data set, and the length unique monkeypox countries told us that there are 32 different countries, and in subtitle I paste together the minimum and the maximum date of confirmation, which means that I get this chart that will automatically, when the data changes, tell me on how many cases it's based, in how many countries, and from which date range. Let's do some mapping next, because that's not that complicated in R and quite informative about showing the distribution of different cases. For mapping you have to load the maps library, and then there is a map data function that creates the world, and I filtered out the region of Antarctica. And what world now looks like is a data frame with 94,000 rows, the longitude, latitude columns, and a region and subregion sometimes. And you see that countries are grouped together. So this shows different points of the borders of the country, the X and the Y values. And if you pipe this data into the ggplot function and you map the longitude for the X value and the latitude for the Y value, you have to keep the groupings, and then you add the geom polygon, which connects each of the points based on the group. So if you would filter the world data for the region called France, it would connect all the points for this region, but with some group specificities. So Corsica is group 556, so only the points for this get connected, but not with mainland France, which is then the group 558. So then it connects all these 615 X and Y values from one to the other, making the map of France. So for this to be more useful, we should see the borders by setting the fill color to a light gray, but keeping black as the outside color. And now this is the map of the world. And in order to add a geom of cases, we would have to do two things. First, calculate a center point of each country, and then add the number of cases to that point. But now I don't have to do that for all of the regions of the world, but I can filter for the ones that also appear to be in our data set. So you can ask the regions of the world whether they are in monkeypox countries, and then you get some trues and false. We can actually do a table on the last value and see that it would then filter the 90,000 rows down to 24,000. And then we group the regions and calculate the mean, longitude and latitude. And I prefer to call them X long and Y lat to remember that the longitude goes on the X axis and the latitude on the Y axis. So then the centroids would look like this. Now we have a center point for each country. So the middle of Germany would be longitude 10 and latitude 50. So it would plot the number of cases right in the center here. But you might also notice that England England is gone now and the United States are missing. This is because we filtered the region based on the country name. And in world, the regions are labeled differently. So for example, it's called USA here and UK, but monkeypox country calls it United States instead of USA. And there is no UK, there's United Kingdom, but most of the cases happen in England. But there's also Scotland and Northern Ireland and Wales, and these we don't find in world region. Here's how you can do the check. For example, you can ask, are the countries in monkeypox actually in world region? And you find some are false. Then you can only look for the unique entries to find out that most of them are included, but there are some false. And with the exclamation point, you switch trues and false. So now we only want to see the ones that are not in the world region, which we can do by indexing using the square brackets. So this vector of trues and false is now applied to the unique number of countries, and it will only spit out the ones that are not in the world region, which also means that we currently could not map them. And we can also look into the subregions and ask, maybe our countries are in the subregions, so please show me the ones that are, and we would get Scotland, Wales and Northern Ireland. So one quick fix to make our countries map the world would be to substitute the name of England for UK, because that appeared in world with the G sub function. We're looking for the pattern England and we replace it with UK, and we do that in the X vector called monkeypox country, and we can do the same for replacing the United States with USA, also the name that appeared in world. So after the replacement, we can create the centroids data frame again, and now it has the UK and the USA with coordinates, which is excellent. Then I created a second centroids data frame that now groups the subregions, but only for the subregions that are in our monkeypox data frame. So now we get centroids 2, which has coordinates of Northern Ireland, Scotland and Wales. And I actually want to combine centroids 1 and 2, but for this we first have to rename subregion to region, because otherwise if we combine those there would be a conflict, because region and subregion are different column names. So I changed the first entry in names of centroids 2 to region, and then you can use the function bind rows to combine both of these to centroids, and now we have good coordinates for the different countries. And all we have to do now is merge the number of cases to this data frame. There are different ways to do that. You could use left join, but a more direct and easy way is to produce a cases data frame that looks like this, a country and N, and then you could match the regions in centroid against cases country. So it's looking for Argentina in centroids, it looks for the name and finds these regions in the cases data frame at these positions, and now you can use these numbers as an index on the N column of cases. Here are the different cases. 214 was England, which is now the UK. And all it does is it aligns the regions as they are in centroids with the country name as it is in cases, and it merges them into another column in centroids. So now centroid has a cases column where we moved the number of cases from the cases data frame to the centroids one. And left join does the exact same thing. So you could have piped centroids into left join cases data frame, and it will look for matching column names. Problem is they don't exist, because here it's called region and in cases it's called countries. If the column names are different, you can use the by function argument to say that in centroids it's called region and it's supposed to match country in cases. And this worked like a charm, because now it finds matching names and it will just join the N column to the data frame. Cases now appears because we already created this column, but otherwise it would move the N's from cases to the centroids column. And now we include this information in the mapping in the following way. We add a geom point, but now we have to use a different data frame, because world was only there to produce the borders, and you can specify the aesthetics mapping in the ggplot function with the data that you pipe in, but you can always use a second data frame, which in this case is centroids, and then the aesthetics mapping will be again the x and y values. Here it's now x long, y lat, and we want to map the size to the number of cases, or n, whatever you have merged to it. So the size of the point will be reflected by the cases, and we have to include group equals region again. But now these black dots aren't super helpful, but the mapping at least works. There are dots everywhere, and we can change the color to red and make it a bit transparent by including alpha 0.5. So now we have red dots appearing on the map, and sometimes they're overlapping here in Portugal and Spain. And there's one problem that you see in the US. The average of the centroid includes Alaska and Hawaii, so the center point moves quite a bit to the left. The next thing I want to do is use the coordinate Cartesian function to change the x limit and the y limit to zoom into Europe. Here we have a similar problem of the average for Norway moving the point up into the ocean. Same for Sweden, it's a bit in the middle. For Germany and France, Spain, Portugal, it works fine. And here we have Ireland, Northern Ireland, Scotland, Wales, and the England average for the UK is up here. A few more things I want to do is use the scale size function to give it a range. So here you can now specify that the cases that go from 1 to around 216 for England, what size the point should take, because by default it will always just go from 1 to 6, but you can blow up the bigger points a bit more by setting it to 10. And now you see the nuances a bit better between cases of 200, 180 and so on. And then I use the labs function to get rid of the x and the y axis labels. And if you want to change the legend, you have to remember from where the legend comes from. And here it is mapped to the size. So within lab, you have to label the size argument. You can change the text to confirmed line break cases to have it look like this. And if you export it to PDF, you get a okay looking map to visualize the number of cases of monkeypox zoomed into Europe. Lastly, I want to look into the age distribution, and here we have a huge gap. So 3/4 of the data have no age next to it. And the reason is, if you count the source of your data, you notice that sometimes it comes from official government websites, but often it's just news related articles where the age of the patient is not mentioned. And in other cases, it's probably just called an adult or middle-aged adult, and then you have these huge ranges. And often they're overlapping, so you cannot really build an average. But what you can do is turn this character into a number. And what kind of works for me and is rather quick would be to calculate the average of the range. So here's a trick I would use. This is the monkeypox age vector with all the entries that are not NA, and you could use the gsub function to substitute values. So first I would extract only the values left of the minus sign, and you could do that by looking for a pattern that is minus and then wild characters and replace it with nothing and do it in this vector x. So then this is what remains. Every time there's a 20 at the beginning, that's what is kept. And you could do that for the other side of the range by substituting the first values and only keeping what's right of the range. And when you do that within a mutate, you can create an age left and an age right column, turn it into number after substituting the values, and then build the average, which is just age left plus age right divided by 2. So now monkeypox has a age new column that's just always the midpoint of the left and the right. It has the following values, and you can pipe that into a geom histogram that shows you a very rough age distribution. It would have been interesting to also look into the hospitalization state to get a grasp of how often the cases were hospitalized or not, but here again we have a lot of missing data. We could have included this information in the cases per country to show country differences. The same for the gender. Here it also a lot of missing data, but more importantly there's almost no spread across the genders, so we could have colored the cases per country by hospitalization state or by gender, but since this is almost 99% male, there's no use in splitting up this dimension. So I hope you learned a lot about analyzing a new data set, making some basic visualizations like bar charts and maps. Feel free to download the raw data over the next days to see if something is changed or added. I will publish the code on my GitHub account so you can modify it and use it for yourself. I hope I'll see you soon for another video here at the Data Digest. Bye bye.